This lecture is a little unusual for an ethical hacking class, since customers don't even like backdoors, let alone rootkits. But rootkits do fit with the objective of the course, which is to provide a path for protection of systems by showing how they can be attacked. And most students who enroll in this course have never really figured out or been taught how rootkits work, so I wanted to fill that gap. There is some system-level programming involved, and you may not have done much of that, but I think there is enough guidance to help you over any rough spots. A rootkit does fit into our ethical hacking methodology in the context of maintain access and covering tracks, but it definitely extends these ideas beyond the boundary normally associated with ethical hacking. Today, rootkits are usually used to hide the malicious actor's presence after an exploit, but they have actually been around for a long while, long before cyber attacks appeared on the horizon. The original rootkits were modified versions of system programs like PS, Netstat, W, and Password that gave the authors root access without the system administrator knowing about it. Today, this kind of precompiled system software is less common in malicious code than hooks that intercept and modify the responses displayed to the user in order to hide a bad actor's activities. Ken Thompson and Dennis Ritchie both received the Turing Award in 1983 for their work on Unix. I want to talk about Thompson for a minute because of his compiler-based exploit against C. To set the stage, he designed and implemented the original Unix operating system and the programming language that was the predecessor to C. During this time period, he actually subverted the C compiler, and he discussed this malware in the Turing Award lecture he gave in 1983. He modified the compiler to detect attempts to compile the Unix logon command and to generate altered code that would accept not only the user's correct password, but an additional password known to the attacker. This is basically a precompiled rootkit. The really interesting idea is the compiler would also detect attempts to compile a new version of the compiler and would insert the same exploits into the new compiler. Furthermore, neither of these attacks was present in the source code and could not be detected by a code review. The title of the lecture, Reflections on Trusting Trust, is an interesting read and is readily available on the internet. Today, rootkits are a form of malware that hides other malicious malware on the system. Basically, they intercept calls to system functions that provide information to the user, and they modify the results displayed to the user. For example, the output of a directory listing or a process listing would be hooked and modified to remove information associated with the malware. So the malware files would not be displayed in the directory listing, and the processes would not be displayed in the process listing. But rootkits are not exploits themselves. A malicious actor cannot use a rootkit to obtain unauthorized access to a system that he has not already compromised. They don't self-replicate, infect other files, or leverage vulnerabilities or unpatched software. Rather, they hide information on a computer that has already been compromised. If you have never read about it, the Sony rootkit is a pretty interesting story. Basically, Sony put digital rights management software on CDs, and that software was designed to prevent copying of those CDs. Of course, they did not inform the consumer in any way of the presence of this DRM software. Basically, when the CD played, the rootkit got installed on the computer. It included cloaking technology to hide files, registry keys, and other system objects from users, and it degraded system performance. It also prevented music from being ripped for iPods, limited copying, and it blocked copying from copies. And of course, once hackers understood what was going on, they found ways to use Sony's rootkit as a backdoor that provided root privileges. Once word got out to the public, it was determined that 3 million infected CDs had been sold, resulting in a class action lawsuit for computer tampering. In the end, Sony recalled the affected CDs and compensated the lawsuit participants with free downloads and cash. The first rootkit on a PC in 1986 was called the Brian virus. It slowed down the floppy disk drive and consumed some memory, making it unavailable to the operating system. It was called a virus at the time, but it was also a rootkit because it intercepted and redirected boot sector read attempts. The malware resided in the boot sector, and the original boot sector was moved and written to another sector where it was marked as bad. If a user tried to read the malicious boot sector, they were redirected to the new location and the original boot sector was displayed. This was early in the timeline for PCs, so floppies were the target. Brian was relatively simple and lacked code for dealing with hard disk partitions, so it avoided infecting hard disks through a BIOS check. As an aside, many viruses at the time did not build in this precaution and clobbered the hard disk, so they were pretty destructive. Brian often went undetected if the user did not notice the slow speed of the floppy disk access, partially due to this deliberate non-destructive approach with respect to hard disks. In about 2003, a rootkit called Hacker Defender became available for download. It was sort of a cookbook approach to creating a rootkit. It came with an installer, which had to run on the target machine, a command and control server, and a configuration file. The user just needed to enter into the configuration file what needed to be hidden. Some of the options were tables, processes, services, and registry information. It was found in the wild for 10 years or so, but the threat has since been mitigated. These are 4 basic types of rootkits that I will introduce at a high level. The lab will require you to write a kernel-level rootkit, which is quite a bit more complex than a user-level rootkit, but provides more capability for the bad actor. Firmware rootkits are persistent because they reside in firmware and can survive the installation of a new hard disk and an OS reload. The attack path is usually via the supply chain, but EEPROMs and BIOS updates are other options for infection. Virtualized rootkits attack the host OS running as a VM on a hypervisor. Basically, hardware calls from the VM are intercepted and modified by the malicious hypervisor. Virtual rootkits do not have to load before the operating system. In fact, they can load into the operating system before promoting it to a virtual machine. The Blue Pill hypervisor, a well-known example, can allow the OS to talk directly to the hardware, or it can shift the OS from having direct control of the physical computer to a VM living under the control of Blue Pill. Once the OS becomes a VM, Blue Pill acts as an ultra-thin hypervisor that lies dormant most of the time, using virtually zero overhead, and waits for interesting events such as keyboard input. The name Blue Pill comes from the movie The Matrix. In this movie, Morpheus explains to Neo that the Matrix is an illusory world created to prevent humans from discovering that they are slaves to an external influence. Morpheus's words to Neo are, "This is your last chance. After this, there is no turning back. You take the blue pill, the story ends. You wake up in your bed and believe whatever you want to believe. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes." So the blue pill leaves you in the Matrix, the red pill takes you out. And I guess Rutkowski's thinking was, once the blue pill was installed, you would be stuck inside the Matrix and not know what is really going on. A kernel-level rootkit has unrestricted security access, but is more difficult to write. The complexity makes bugs common, and any bugs in code operating at the kernel level may seriously impact system stability, leading to discovery of the rootkit. Bootkits, a subcategory of kernel-level rootkits, compromise bootloaders for machines with full disk encryption to intercept the encryption keys and passwords and persist into protected mode. An application-level rootkit is operating in user space, so it is easiest to write. The main approach is to inject DLLs into other processes to intercept and modify API behavior. Kernel-level rootkits can also be implemented as DLLs, but as with Linux, you need root access to modify kernel behavior. First, the attacker has to get a wrapper program to execute. When it does, the wrapper extracts the DLL file and maps it into memory as a module and calls one of the functions to install the rootkit. Since this requires root privileges, either you have to escalate or leverage a vulnerability to be able to inject the executable into another process. In the case of Stuxnet, the installer actually got injected into the antivirus software running on the target to help circumvent detection. By the way, Stuxnet also had a user-level rootkit used to hide activity in the programmable logic controller. This was a brief introduction to the history of rootkits. Now we want to start down a path of developing a simple kernel-level rootkit, starting with the basics of kernel-level programming. Kernel-level programming is necessary to develop a kernel-level rootkit. Even if you are a C programmer, you may not have had much experience with this. Unfortunately, what is covered in this module will just scratch the surface, but it should be enough to get the rootkit working and understand the fundamental ideas. I took most of my material from Basics of Making a Rootkit from syscall to hook, but I am not positive Donuts is the original author. It seems to have been reposted many times by people claiming authorship. At any rate, between the article and this lecture, you should be able to find your way through the lab. By the way, there are many syscall tutorials on the internet, but I did not find any of them very helpful. As a result, I had to debug those elements of the rootkit development piece by piece, and you may have to do the same, especially if you choose a different VM for your target. These are the topics we will cover in this module. When we actually start to explore system calls, we will need to rebuild the kernel. So you will want to create another VM that you can reload if that process does not go smoothly. We will also explore loadable kernel modules, which are similar to DLLs on Windows, and will actually hook the system calls. As we proceed, you will see that root access is critical to the creation of a kernel-level rootkit because the LKM needs to run with kernel-level privileges. The end game is to develop an LKM to hook a PS call and hide one of the running processes. The first step is to understand the difference between kernel space and user space, as the hooking takes place in kernel space. While we have a pretty good intuition about what system level means, I want to start by diagramming exactly what takes place where. The first important idea is that processes running in kernel space have unrestricted access to memory, while processes running in user space do not. This, of course, is what you would expect to keep user-level processes from trampling on each other. But a user process sometimes needs access to system calls, and to facilitate this, the kernel exposes interfaces to the user for functionality, like opening a file in the file system. And a point you may not have understood is that root-owned processes actually run in user space and use the same system call API. Root privileges are far different from system privileges. Root has more permissions than a standard user, but a root process still runs in user space. This is a diagram that shows the kernel has access to all the memory, while a user, even UID 0, does not. The kernel exposes the syscall interface to user space, and the system calls ask the kernel to provide the service through the interface. You will see this picture again when we talk about hooks into the kernel. To start off, we are going to create our own simple system call so that we understand the details of how it works. At the end of the module, we will hook an actual system call built into the kernel by developers. This approach of creating our own system call first means we are going to have to rebuild the kernel. I recommend you start with a VM you don't care about in case it gets corrupted. It is possible to take a snapshot of one of your existing VMs, but my conservative approach was to use a separate VM for a couple of reasons. First of all, you probably did not download the source for the VMs you have already installed, and if you do that now, it is totally unclear how the source will align with the patches you have put in. You definitely want to run apt-get upgrade before proceeding to make sure you have the latest package list. If you install a new VM, you may not want to patch the kernel for this lab because kernel source that has been patched in various non-standard ways may cause problems. For our purposes, we don't care about the patches anyway. Second, an older version of Linux may be easier to understand and work with than the most recent version of Ubuntu. In my case, I used an old Debian VM. You don't have to use Debian, but you will need to sort out the management of system calls, which may be handled differently. Even a different version of the same OS can have the system call tables organized differently. The assumption is that at this point you have installed the VM and updated the package list. The next task is to download the source so you can recompile the kernel. You can download the source for the whole build or just the kernel source. Here is syntax for either approach. If you just want to download the kernel source, be careful that what you request from the kernel archive is precisely the version of Linux you are running. Although downloading your version will most likely be different than in the syntax shown here, it might be a good learning tool to visit the kernel archive and see if you can find the kernel source as shown in the wget statement. As noted, the source usually needs to be in /user/source, but you should confirm that this is the case for the version of Linux you have decided to use. Here is the syntax for untarring the kernel source downloaded previously to that location. After the tar command runs, the subdirectory is identified by the kernel version number. I used an old Debian VM since it was already installed in my virtual hacking environment, and I had been thinking about deleting it for some time, as Squeeze is now deprecated and archived. That means this build had been patched many times, and I had no problems with source mismatch, so my earlier cautions may not be critical, at least for the kernel source. When I visited the Debian website, I saw the recommendation to use the Synaptic Package Manager rather than wget to download the source. So I started the package manager, searched on kernel, and found the Linux source I needed. Once I added the package, the README recommended not using /user/source, so I put it into /root. You may encounter the same kind of differences for the VM you choose. Work methodically so you know your kernel recompile will not go astray. In fact, it may be worthwhile to rebuild the kernel at this point to make sure everything is working properly. This screenshot shows my search for the kernel source using the package manager. The description actually says it contains all the Debian patches. So you definitely want to run apt-get update to align the current package list with your build. This screenshot shows the tarball and the source after untarring in root's home directory. These are some additional packages that are required to rebuild the kernel, and using the package manager instead of apt-get is probably the best approach for all of these, as the package manager does a really good job of resolving dependencies. So the packages you want are build-dep, kernel package, and libncurses5. You may not need build-dep if you are using the package manager, but the other two are definitely needed to create a custom kernel. I have explained the difference between user space and system space, noting that root is just another user with additional privileges. I have also discussed the steps for downloading the source and additional packages you need to recompile the kernel. Next, I will talk about system calls and a specific system call we will add to the kernel of our VM. Now we are going to add our own system call to the kernel and then recompile the kernel. The simple syscall will be called pname, and it is a very simple program. used to pass in a process name on the command line and have the process ID written to the terminal. When there is more than one instance of the process, you will get a PID for each. To start off, we need to create a new directory for our program. Since the program is called pname, we need to create a pname subdirectory in the source tree. There will be two files in this directory: the program itself, pname.c, and the makefile to compile the program. To be clear, this makefile will not be compiling the kernel, just the C program. This shows my source directory for pname, and you can see pname.c and the makefile. Ignore pname.h for now. I believe this is a bit of a red herring in Donut's paper. I did not find it necessary for compiling pname, but keep it in the back of your mind in case you have errors when you try to build the kernel which will run the makefile to compile pname. These are the headers to include in pname.c. Be careful about cutting and pasting because of the stylized characters that PowerPoint and Adobe Reader may use. I recommend you take the code from the zip file source repository. This is the first part of our program. ASM linkage is a keyword for a system call that defines how parameters get passed. Notice that the name for the call starts off with sys_, which is important for keeping track of system calls. Also, the open bracket is not closed on this slide, but will be closed on the next slide at the end of the program. If you don't have much experience with C, these are simply the structures for managing the data. Task contains the names of the processes running. TTY just keeps track of the terminal for printing out the PID, and name is storage for the PID for printing to the TTY. This is where the conversion from process name to PID takes place and where the results are sent to the screen. The system call accepts a process name from the calling program and compares it to a list of running processes. So the system looks at the process scheduler and compares the running process names with the name passed in. If it finds a match, it prints out the PID to the user's terminal. So the loop, depicted here in green brackets, cycles through all the running processes, and the red brackets are commands to print the PID when a named match is found. In the sprintf statement, the LD format is just for long decimal, which is how the PID is held in the kernel task structure. And the sprintf behaves like printf in terms of format statements, but in this case puts the PID equal into a string buffer pointed to by the name, and appends a null automatically when the string ends. Finally, it uses the write command to write the string to the screen. But since the kernel is doing the writing, it needs to determine the user's TTY to make sure it goes to the right place. This is just a screenshot showing the source on my VM. And the makefile is a simple one-line file. It is in a subdirectory under source, and it is going to be called by the kernel build program's parent makefile. This is how the kbuild recompiles the kernel. It runs through all the source subdirectories and finds all the objy files first. Then it compiles each into an object file. Once they are all compiled, a loader program merges the individual object files into a single object file called built-in, which is not a loadable file. Finally, built-in is linked into VM Linux by the kernel's makefile. I've explained the workings of the custom system calls, and I have described the recompile process at a high level. But at this point, pname will not be built when we recompile the kernel. We still need to tweak a couple of system tables to facilitate that. We have created the custom system call, but there is still much work to be done to get it to build with the kernel. The system tables need to have the system call added, and the kernel makefile has to have the new program added to it as well. These are the adjustments we have to make to build a customized kernel with a new system call pname. Steps 1, 3, and 4 are pretty straightforward, But step 2 will be complicated because your build will probably handle system calls differently than mine, and probably differently than the version discussed in Donut's paper. That means you are going to have to do some critical thinking, inject a little Google foo, and just plain analyze the kernel tables to get the call to work. The first bullet tells you where the kernel's makefile should be located, at the top level of the source tree. A reminder, the Debian website said not to use /user/source, so I put it in root's home directory. Once you have located it, edit this file and make one change. Add pname/. You should be able to do a search on core tac-y and find the line quickly. Then just add pname/ to the end of the line. This tells the compiler to look in the pname directory for the child makefile. This is a screenshot of my makefile with pname added. Again, the caution, it should be pname/, not /pname. Next, we have to add pname to the syscall table so it has a call number. This is where everything gets tricky. This slide will describe the process for Linux 3.16.36, and the next slide will describe it for Linux 2.6.32. Your call table structure may be completely different, and if that is the case, you will need to figure out what to do. The discussion forum may help, but do some digging on your own and don't depend on that. For 3.16.36, the system call table can be found at arch x86 syscalls from the top of the source tree and is called syscall_64. You need to identify the last call number in the table and increment it by 1 for the pname system call. In this example, the last system call was numbered 319, so the new entry would have 3 elements: the system call number, the C program name, and the system name given in the ASM linkage call prototype. So for 3.16.36 build, the entry would be 320 space common space pname space sys_pname. Unfortunately, this may not work for your build. For my older Debian build, the system call table was in a slightly different location, and the file name was quite different, including the file name extension, which had changed from .tbl to .s. I wasted some time trying to find it by searching for syscalls, plural rather than syscall, and I can think of many ways this might be modified. So be creative if you have trouble finding your syscall table. One useful approach might be to search the internet for system call tables combined with your Linux version number. Hopefully a search like that will return the file name. The complication for me was the syscall entry was broken into 2 pieces, not a single entry as with version 3.16.36. The prototype name went into the syscall table, but the call number was defined in a header named unistd_32.h, which required 2 changes. I had to add the new system call entry and also increment the number 4 in our _syscalls. Finding this link between syscall_table_32.s and unistd32h was a challenge, especially since they were in totally different parts of the directory tree. This is a screenshot of my syscall table with the new entry. I just followed the pattern for the rest of the table. And this is a screenshot of the updated header file. Again, I just followed the pattern for the changes. The third task is to add the name for our syscall prototype to the syscalls.h file. Fortunately, my syscalls.h was in the same location as 3.16.36, so the change was easy. Just add the prototype from the pname source to the header file. This basically tells the compiler how this system call passes parameters. And here's a screenshot of my syscalls.h file with the prototype name for the new system call. And that's it. However, before we can compile the kernel, we have to run make menuconfig, a tool used to configure Linux source, a necessary step in compiling the source code that will allow the user to choose the features and options of Linux that will be compiled. In our case, you should be able to just accept the default configurations when prompted by make menuconfig. Now you can start the kernel recompile by typing make from the directory where you found the kernel's makefile, probably the top level source directory. The build is going to take a while, so watch for immediate errors and then go get an espresso. Once the kernel is built, you need to install the new version with the command make install make modules _ install. I actually ran the installation with separate commands, but combining them into one should be fine. After the new kernel is installed, cross your fingers and reboot the system by typing reboot. Once again, my old Debian build did not make things easy. I got a kernel panic telling me the kernel could not mount the file system. It turned out that a file was missing in the boot directory. I'm not entirely sure why this happened, but the good news was it was not a rare occurrence, so I was able to find some guidance on the problem. The fix was pretty simple. There is a program available to recreate the init.rd file. Why this is not part of the build script is kind of a mystery, but this is the reason it may pay to create a new VM for this lab, just in case you can't recover from a panic error. This is a screenshot of the boot directory after the init.rd file was recreated. Depending on how your system loads, you may need to update the bootloader. In my case, update-tat-grub did the trick, but it is possible you will have to update 2 grub files manually to add back in the init.rd location. Finally, you will most likely have to select the new kernel from the bootloader menu, as the system will automatically boot with the last kernel used. The bootloader does not look for the most recent compiled kernel. Now we need to create a simple C program to test the system call we just added to the kernel. These are the headers for testpname.c. Notice the unisted.h header. Recall that is where the new call number is found on my old Debian system. This is a simple program that prompts the user to enter a process name, reads the user input, parses a string, and creates a token. Then the system call is made by the number we added to the syscall table, and the process name is passed to it. The system call prints out the PIDs and then passes status back to testpname. Compile this simple program with the GCC compiler. Then open 2 terminals. In the first one, run testpname and enter the name of the shell you are running when prompted. In the second one, list the running processes and grep on the shell name. You should see testpname displaying the same PIDs as PS. If not, you have a problem and need to review everything above. Here is a screenshot of testpname's output. I was using bash on Debian, and you can see I had 3 shells running. The system call printed the PIDs to the TTY and returned no errors to the calling program testpname.c. I have talked about the places that pname or sys_pname have to be added to get the system to see and build in the new system call. And I described the problems I had to solve to get the build to complete. Hopefully this will help, and your recompile experience will go more smoothly than mine. Once the kernel had a new system call, we were able to create a simple program to call it, testpname.c. Next, we will discuss loadable kernel modules. Loadable kernel modules, similar to Windows DLLs, are object files that contain code to extend the running kernel. LKMs sometimes add device driver functionality to support new hardware or file systems, and sometimes they add system calls. When they are no longer needed, LKMs can be unloaded in order to free memory. The key for this submodule is they extend the kernel, and we will leverage that for a rootkit. This is a list of LKM properties. The fact that you can extend the kernel without recompiling is incredibly useful. In Windows, it is not even possible to recompile the kernel, so without the capability you would have minimal flexibility, and you would be constrained for the most part to what Microsoft provided. Linux is not as problematic as it is open source, but rebuilding the kernel doubles the risk when compared to just writing an LKM. Of course, LKMs are risky on their own if care is not taken. For example, when developing one, a pointer mistake could wipe out the file system. But the most important property is LKMs run in kernel space. so they have access the user programs do not. And if a bad actor has root privileges, it is possible to load an LKM and run code in kernel space. I am going to discuss a loadable kernel module called hello lkm.c. Any LKM has a few mandatory components in order to qualify as a loadable module. First of all, it must include the module headers in order to get everything to resolve when it compiles. In our example, we also need the kernel headers, but only because we need support for the macro expansion of the kernel's printk function. The license line is required as well to avoid tainting the kernel when the module loads. This isn't critical, but when tainted, it means the kernel in that configuration with the LKM loaded is not supported by the community, and you will not be able to get any support from kernel developers. LKMs also need an initialization section and an exit section. Init underscore module either registers a handler with the kernel or it replaces a kernel function with its own code, and then, in many cases, finishes initialization by calling the original kernel function at the end. The cleanup module is supposed to undo whatever the init module put into place, so the module can be unloaded safely. And a reminder, you don't really run an LKM. The code making up these functions executes when the module loads and unloads. This is a very simple LKM. It has all the mandatory parts just mentioned, and the initialize function is simply a print statement. Since it does nothing when it initializes, there is nothing for the exit function to clean up, so we just add another print statement. A couple of comments though. First, the print statement is printk, and it is only available to the kernel. It accepts a format string like printf, which specifies how to render various data type parameters into a string. The string is then printed to the kernel log. The second thing to notice is kerninfo, which is a keyword for log level and specifies the type of message sent to the log, in this case simply some information. There are 8 log levels, which I will discuss in a minute. Suffice it to say for now, we are just printing information to the log. If we didn't specify kernel level in the printk statement, it would default to a kernel warning. And notice the syntax. There is no punctuation between the kernel level and what we want to print. If we were to load this LKM, we could see, quote, hello kernel, unquote, in the kernel log by entering dmesg at the command line. Once the kernel is ready to compile, this is what the makefile would look like. However, this is not a traditional makefile because loadable modules are more like the kernel and not so much like a user program. What that means is the kernel build system handles part of the module build. The first line states that there is one module to be built from the object file hello lkm.o. Although not identified in the makefile, the resulting module is named hello lkm.ko after being built from the object file. In the second line, when the compilation starts, the tac-c changes the directory to the kernel source tree because the build system needs to find the kernel's top-level makefile. Then the m equal option causes the makefile to move back to the module source directory before trying to build the module target. This target in turn refers to the module found in the objtacm variable, which is hello lkm.o. So it is pretty confusing if you haven't seen it before and don't work with it. But if you are interested and want additional detail, the files found in documentation/kbuild directory in the kernel source tree should help. These are the commands for loading and unloading an LKM, and pay attention to the fact that we load the .ko kernel object file, not the .o object file. insmod is considered to be a rather simple program that does not address dependencies or print out much in the way of useful error messages, but it does load kernel modules into kernel address space from user space. Modprobe is considered to be a better tool, but for our purposes, insmod is good enough. Insmod tries to link a module into the running kernel by resolving all symbols from the kernel's exported symbol table. It also relocates memory in the event the kernel does not have enough contiguous physical memory to accommodate everything in the module. Once the relevant sections are loaded in memory, the kernel calls the init routine of the module. This is a screenshot of a listing of hello lkm.c on my system. You are not stuck with names like init module and cleanup module for the initialization and cleanup. You can name them anything you like. You just have to provide module definitions to identify which function is for initialization and which is for cleanup. That is what the last two lines do. This is just a short introduction to printk, the kernel utility that prints to the kernel log. Log levels are defined in linux/kernlevels.h. And which log levels are printed is configured in the file sysctl located at /proc/sys/kernel/printk. The thing about log levels is some are printed to the console in addition to the log, and some are only printed to the log. Raising the log level to kern alert makes sure it writes to the console. If you don't specify a priority level, the default priority, default message log level, is used, which just writes to the kernel log. This is a list of log levels and what their intended use is. As I just noted, you have to set the log level to kernel alert to ensure it goes to the console, notifying the user. Otherwise, it will probably just go to the log, depending on your sysctl settings. When hello LKM is loaded and initialized, little happens. Nothing shows up on the console. The LKM is basically loaded into kernel memory, awaiting a system call. But when loaded, the initialization routine does run, so the printk should write to the kernel log. That means as soon as it loads, even though nothing else is happening, we should see hello world in the log, and can verify that by typing dmessage at the command line. As noted earlier, printk does not interact with user space, so nothing shows up on the terminal. If you change the printk statement to send an alert at kernel level 1, it would be printed to the console, but not to the terminal. Actually, messages with a value lower than the console log level will be printed to the console, and you can determine your current console log level by entering cat/proc/sys/kernel/printk, and 4 integers will be returned. The first integer shows you your current console log level, while the second shows the default log level. To change your current console log level, you would just echo 8 into /proc/sys/kernel/printk at the root level command line, and every kernel message will appear on the console. Another way to change the console log level is to use dmessage with the tech-end parameter. All messages go to the kernel log, and you can see them with dmessage, but they may also go to /var/log/messages if syslogd or klogd are running. Once the LKM is loaded, it is possible to see it and any other LKMs loaded using the list module command lsmod. Two other interesting commands are modinfo, which generates information from the module keyword in the LKM, for example, author, description, license, version, and info, may all be provided via the module keyword. And rmmod is used to remove the LKM. This screenshot shows 4 things. First, I ran the insmod command, and then the lsmod command in a different terminal, which shows hello LKM has been loaded, along with several other LKMs. Next, I ran rmmod to unload hello LKM, and finally, the dmessage command in the third terminal shows hello kernel and goodbye cruel world have both been logged to the kernel log. This has been an introduction to LKM basics, and in the next submodule, we will hook a call to our custom syscall pname using an LKM. So now we are going to build an LKM that will hook our custom system call pname with the final goal of being able to use the same approach to hook any system call that comes with the kernel. You've seen this diagram previously, but I've added 2 pieces. First, I show pname, which is our kernel-owned system call that has access to all of the kernel space and the entire machine's memory. Second, I've added the kernel log, where all kernel messages will be written. and users can read the log using dmessage. Notice we can call pname from user space, just like we call any other system call exposed by the kernel. And expanding this picture, I have added the malicious LKM we want to construct in this submodule. It will run in kernel space and hook all calls from user space to pname. Again, it will be running in kernel space, so we do need root access to install the LKM. It works like this. First, the LKM is loaded, and it is just sitting there waiting for a call to pname. When pname gets called from user space, the LKM intercepts the call and executes some malicious activity. In our case, it will simply write to the kernel log to demonstrate the hook. Then the LKM makes the original syscall to pname as originally requested from user space. So the fundamental concept is the LKM becomes a man in the middle between user space and the system call. How do we create an LKM that can intercept a system call? The first step is to save pname in the LKM so that when the hook is finished, we can call pname and return the expected response to the user. We used a variable custom_syscall to save the name of the system call we created. Then we changed the syscall table to point to the hook inside our LKM instead of the system call. That means when a user calls pname, the call will be diverted to the hook. And when the hook is finished with its malicious activity, it knows where to get the name of the original system call because it is stored in custom_syscall. Once the calling sequence has been modified, the LKM just waits for a user to call pname. First, we want to get the address of the system call table so the LKM can modify the call to pname. We will hard code this address into the LKM for simplicity, but with some enhancements, the LKM could be modified to determine the address on the fly. The address in my 32-bit Debian system is hex 126A280. Yours will be different. This header list is the first part of hook.c, the LKM that will intercept our system call pname. This is the second part of the LKM. It includes the module information. And there is a comment identifying the hard-coded system call table address. But for now, the variable is just declared as an uninitialized pointer. We also identify the system call prototype for the syscall the user requested that we want to call after the hook is finished. The third snippet of code is the call to the malware function, which, for our purposes, just prints to the kernel log so we can verify that the call to pname was hooked, but the program could have executed any code it wanted. Then, after the hook executed, the LKM makes the original call so the user is unaware of the hook. This part of the LKM is a little tricky, as we are modifying the kernel system call table permissions, and you would need to understand the details of the page table entry structure to figure out how to do it. While it is unlikely that any of you are system programmers, given the code, it is easy to see the function make_rw consumes the address of the syscall table and changes the permissions to read-write. And this snippet just reverses the code on the previous slide and returns the syscall table to write-protected state when we are finished. The initialization code prints to the log when the LKM initializes, and then the hard-coded system call table address is set to match the hex value we determined from the system map. Next, we save the call table information for pname in custom syscall. Finally, we disable page protection and replace the system call table entry for pname, allowing us to execute the hook prototype defined in this LKM. We are really replacing the custom syscall defined when we built the kernel with a malicious syscall defined in the LKM. Once we make this change, the LKM just waits for a pname call to come in. When it does, the call is intercepted because of the change to the call table, and the user space request to run pname is diverted to the end of the hook malware section. The first thing the hook function does is to print a message to the kernel log, which tells us the hook function ran. After the hook function prints to the kernel log, it calls pname, thus returning to the user the requested output of the system call. This is the exit code, so it runs when the LKM is unloaded. First, it prints to the kernel log a notification that it has been unloaded. Then it restores the system call table to its original state with write protection. The code may seem complex, but it is not critical that you understand every detail. On the other hand, good ethical hackers have to be able to roll up their sleeves and dig down far enough to understand the details when necessary. It is worth reviewing the code a couple of times if necessary, as you won't find a much simpler example of kernel hooking code. This is the makefile for the hook, and it is exactly the same as the makefile for hello LKM, so I won't go over it again. The next step is to test it and see if it worked. First, compile the LKM using the previous makefile and load the LKM into the kernel. Dmessage will tell you if it loaded successfully. Now the hooking LKM is loaded and waiting for a call to pname. So let's make a call. Run test pname and enter a process name. You should get back the PIDs in the terminal, but after the load, dmessage should show you that the hook intercepted the call and wrote to the kernel log before calling pname. Here is a screenshot of a successful LKM hook. It does not show the compile step, but it does show the LKM being loaded in the top left terminal. The top right terminal shows that the kernel recognizes the LKM in memory. The second terminal on the left shows the execution of test pname and the expected results being printed to the screen. The bottom left shows the LKM being unloaded, and the bottom right is a look at the kernel log, which confirms the LKM was loaded, that it hooked the system call to pname, and it was successfully unloaded. The TP1 in the kernel log is just a test point I added during debugging. That finishes off the discussion of how to construct an LKM to hook a system call. In this case, we modified a custom system call that we added to the kernel. Now we want to use the same technique to hook a standard system call. Specifically, the process listing called PS will be hooked to modify the listing of running processes provided back to the user. In this lecture, we will discuss how to modify the hook from the previous submodule to intercept a user request for a process listing and return a slightly modified listing to make the process SU appear to be just another bash shell. For simplicity, we are actually going to hard code the associated process IDs into the LKM, but some system level programming could make this a dynamic determination as well. The trick will be to use a hooking LKM, as discussed previously, to hook a request to the open function. PS calls open because it needs to open the process file maintained by the kernel to provide the user with accurate information about running processes. Once the open is hooked, the LKM will change the path name for the process that we want to hide to the path name for the process that will hide it. Thus, the information returned will be for the wrong process. In order to simplify the LKM code, we will hard code the information about processes of interest, but again, these could be determined dynamically by a good system programmer. So we will use PS to get information about the SU process which we want to hide. We will also use PS to get information about the bash process that we will use to hide the SU process. This does fit into the category of a kludge, but it should not detract from the learning process to do it this way. It just isn't very elegant. These are the changes we need to make to the hook program to get it to work. The complexity of this task will depend on your understanding of the previous submodule. If that wasn't crystal clear, I recommend you go back and review the content again. If you did not understand the hook, it is highly unlikely you will understand the changes we will make here for the new LKM. First, we need to change the path name that the open command will use to gather information on processes to provide it back to the user. Second, the LKM init routine needs to be modified to change the syscall table for a different system call, open rather than pname. So the LKM isn't really very different from what we have already discussed. I will only give you some of the details here because one of the challenges of the Rootkit lab is to understand this well enough to get it working. These are the new kernel-level function prototypes for the LKM-defined system calls. The first function saves information about the original call to open. As before, the hooking component wants to return to this call when finished executing the process hiding routine. Basically, the function original open replaces the custom syscall function in the hook. The second function adds the hook's simple print to the kernel log, but then actually does something malicious. It changes the path information for the process that is to be hidden so that open returns information about the wrong process. The hijack basically replaces the hook. It still prints to the kernel log so we can verify the hook, but it also finds the path to the process to be hidden. In the path name being passed to the open, the process to be hidden has its path name replaced with the path of the process we want to use to hide it. So the path name string passed to open will no longer have the PID for SU. It has been replaced with the path name and PID for bash, thus returning the wrong information. This is the LKM's initialization routine. The important changes are highlighted in red. First, we need to save the original call to the open routine so it can be used later. The second change is to redirect the open system call to the hijack system call defined in the LKM. The technique is exactly the same as used in redirecting pname, but the line in the system call table is different. The exit routine restores the original open system call, makes a table read-only, and prints a message to the kernel log indicating the uninstall went smoothly. Many details have been left to the reader, but this screenshot shows a successful hijack of the process listing information. In the top left terminal, at the before arrow, you see the PIDs for bash and SU, which represent the processes at the beginning. In the bottom left, you see how these will be hard-coded into the LKM to hide the SU process. The red and green arrows show how those PIDs match. After making the change to the path name, bash's PID gets passed to the open command instead of SU's PID, and as a result, incorrect information is going to get returned to the user. Going back to the top left terminal, you see the results of running PS after the malicious LKM has been loaded. The SU process is gone, and in its place we see the bash process. Because we were not creative in our string manipulations, we see the same PID listed twice, the original and the one we copied to hide SU. This could be tweaked to render a different number for a different process. The fact that the same PID was rendered twice, one line after the other, would make any user suspicious. But we should be able to fix that. For us, the important idea is not the PID value, but that we were able to modify the PS result sent back to the user by hooking open with an LKM. We have just finished developing a rootkit that modifies the listing of running processes. The results presented to the user could be fine-tuned, but the foundational idea about hooking system calls to make changes should be clear. LKMs and DLLs can behave maliciously, and we probably wouldn't even know they were there. Next, I will discuss buffer overflow and return-oriented programming. This is actually 2 to 3 lectures compressed into one, so the time involved and complexities may be even greater than usual. Please get started early if you have opted to do one of these labs. This module and a subsequent module will discuss operating system security. In this module, I will talk at a high level about some well-known OS exploits, and then we will do some hands-on examples exploring the issues around set UID. The subsequent module will focus on buffer overflows, mitigations, and subsequent extensions of the exploits, leading to a discussion of some current approaches. The bootloader demo isn't using an exploit. It leverages functionality built into all OSs in one form or another that can be exploited if you have physical access to the computer. For Linux, when a computer starts, it runs a program called init, usually found at /bin or at /sbin. This program is responsible for the system startup and creating usable computing environment. However, we can change that and start with a program other than init. For example, specifying init equals /bin/bash tells the kernel to run bash instead of init. At the same time, if we change the permissions from read-only to read-write, we are telling the kernel to boot with the file system in read-write mode instead of read-only mode. Traditionally, the kernel starts with the disk in read-only mode, and later on a process checks the integrity of the disk before switching to read-write mode. When you initialize with bin bash, the services that would normally be started by init are not running because the shell doesn't start any of those OS services. In some cases, normal file system mounting based on the entries in etc fs tab is bypassed, as well as any options listed in etc init tab, which include the system's default run level, what processes to start, and what actions to be taken when the system enters a new run level. If init tab is not processed, single user mode is probably not secured. Run levels determine which programs run when you enter that run level. These are the 6 run levels on a Linux system. 0, 1, 2, and 6 are pretty standard, but levels 3, 4, and 5 may vary. On some systems, they are identical to level 2, but on some systems they differ. The files that identify which programs will run are located in /etc. For each run level, there is a file named rcx.d, where x is the run level. So to see what programs execute on a normal boot to run level 2, cat /etc/rc2.d. This slide shows the steps you would go through to get a root shell using an unprotected grub bootloader. As mentioned earlier, since /bin/init has not been run, you will be running at level 1, where not all of the services have been started. And in some situations, it may be only that the root file system is mounted, which means you may have to mount other parts of the file system depending on your objectives. For example, you might have to mount /proc. If you don't change permissions and mount the file system as read-only, you will also need to make the root directory editable by typing mount tach-o remount, rw/. If you try to unmount followed by mount rw/, you kick the ladder out from under yourself on the first command. If you read about this functionality on the internet, you will find that many references to the file system being mounted as RO. But as you will see in the next screen, that is editable in some Linux versions. You should try this if you installed grub or lilo with any of your VMs. If you do try it, once booted, you can find lots of information at the command line about what file systems are mounted. This is how grub will normally present the boot line. Notice your file system starts off read-only, and what is printed to standard out is minimal, as denoted by the quiet command. More information will be printed if you do not use quiet. The directions for editing the boot script are at the bottom of the screen. For my instance, pressing E puts me in the edit mode, and I can edit the script. In this screen, I have changed RO to RW, deleted quiet, and added init equals /bin/sh as the initialization program. You could also set init to /bin/bash, but I have bash symbolically linked to sh, so the effect is the same. Control X resumes the boot process and puts me into single user mode at the command line with root privileges. This image shows a request to read the shadow file to demonstrate that we are really in root mode. Here you see I have catted the shadow file because I have root privileges. Normally /bin/init executes scripts as needed and as run levels change. These scripts set up all the non-operating system services to create a user environment. We forced /bin/sh to run instead of init, which left us in run level 1, but the RW entry mounted the file system as writable. Now we can just type passwd and change the root password to anything we like. When we reboot and log in as root, we have normal root access. For my instance of Debian, /proc is also mounted. But if it is not mounted in your instance, you may need to mount it yourself with a mount/proc. What is the /proc directory and why is it important? /proc is very special in that it is also a virtual file system. It is sometimes referred to as a process information pseudo file system rooted at /proc. It doesn't contain real files, rather it has system runtime information for the kernel, sort of a control and information center for the kernel. Many system utilities are simply calls to files in this directory. Because the proc file system exists only as a reflection of the in-memory kernel data structures, it displays most files and directories within /proc as having 0 bytes in size. This summarizes the options for determining what file systems are mounted, but they all behave slightly differently and provide different information. /etc/fstab is read by init and maintained by the system administrator. Since init does not run in our bootloader example, the contents of this file are not too useful. However, if the system booted normally, it provides a list of all file systems that should have been mounted when the system booted. /etc/mtab shows what files are actually mounted, and it is updated by the mount and unmount commands. /proc/mounts also lists all the mounted file systems, but it is controlled by the kernel and should really be the authoritative source. You should expect mtab and mounts to agree, but they could easily be different than fstab. Here is an example of why single user mode can be helpful. I was switching the symbolic link for /bin/sh from bash to Z shell, which we will discuss in a subsequent submodule on setuid. But when I did that, I got myself into a fix by deleting su when I meant to delete sh, the symbolic link. I was lucky I had a copy of su on my disk in my home directory, but I didn't have the privileges to change ownership or move it into /bin. Single user mode gave me root and saved the day. So a bootloader without a password can provide an attack vector if you have physical access to the box. Each OS has something similar to a single user mode, but the behavior and configurations are slightly different. On Mac OS, single user mode will let you change the password, and it also gives you access to disk repair utilities and the password hash for offline cracking. That means you don't have to take any action that might alert the administrator, like changing the root password. In Mac OS, this single user mode functionality can be protected with a password. You have seen an example of how you might abuse the Linux single user mode, but you can guard against that with a bootloader password. Once you set a password, you cannot edit any grub entries or pass arguments to the kernel from the grub command line without entering the password. The bootloader password solution for Debian Sweezy, which I am running, uses MD5 encryption for confidentiality and requires editing the /boot/grub/menu.list file. Hopefully more current versions of Debian use a stronger hash function. In Windows, an administrator using the recovery console gets read-only access to all volumes except for the boot volume, where he can write as well. But even on the boot volume, he only gets write access to the root directory and to the Windows system directory. The grub configuration resides in /boot/grub/menu.list and already contains documentation on how to set a password. This submodule shows the importance of protecting access to single user mode because it includes root level privileges. The functionality is important because it provides a maintenance mode for multi-user environments where some admin tasks require access to shared resources. Since network services are not run, this mode eliminates any possible remote network access, providing some enhanced security, at least temporarily. However, with physical access, you can use this mechanism to recover or change a root password. Sometimes we need a single user capability, but at the same time it introduces a security vulnerability. In the next submodule, we will discuss trust and the operating system. In this submodule, we will talk about trust and the operating system. I debated about whether to use the title Trusted Computing or Trusted System for this submodule, but both have somewhat specific connotations. Trust in the OS is a better description. However, in this module, I will talk about trusted computing as defined by the Trusted Computing Group and a little about trusted system, which is a system that is relied upon to enforce a specific security policy. This graphic provides a notional view of some of the protection mechanisms used by an OS. In this case, the OS is managing three processes. It provides access to resources, schedules access, and enforces access control. The OS provides processes with efficient resource access mechanisms for access to the file systems, memory management systems, network protocol stacks, and system displays. It switches among the competing processes fairly to ensure that all processes get equal access to computer resources and there is no starvation. And it provides secure execution so that the access to resources is controlled to eliminate conflicts so processes don't interfere with each other. The Old Orange Book, or Trusted Computer System Evaluation Criteria, defined trusted computing base as the totality of protection mechanisms within a computer system, including hardware, firmware, and software, the combination of which is responsible for enforcing a security policy. Of course, that was written in 1985, but it is still relevant today. The critical software modules trying to ensure a minimal approach are the modules to get the computer started in a secure way and then maintain a secure posture by enforcing security policy to ensure movement from one secure state to another. Once the Trusted Computing Base, or TCB, has been identified, it must protect itself with a strong boundary represented by the green box. Any code trusted by the TCB must become part of the TCB. Any code in the TCB that gets corrupted and is untrusted causes the whole TCB to be corrupted. The idea of trusted computing is now based on ideas and specifications put forth by a consortium of technology firms called the Trusted Computing Group. One of the specifications put forth was for the Trusted Platform Module, or TPM. And nearly every computer built today comes with a hardware implementation of that specification, although it is seldom used. The TPM is a hardware-based root of trust designed to ensure that a computer boots securely and stays secure after booting. The TPM specification defines three fundamental services, which we will discuss next. The Authenticated Boot service uses digital signatures on the code base to ensure all the code comes from a legitimate software vendor with valid certificates. The service also logs attempts to tamper with any part of the configuration or replace loaded modules so that the evidence can be reviewed as necessary to identify potentially malicious software. The trust boundary can only be expanded if the new code also has a validated signature. Of course, the Flame virus was spread because malicious code had a bogus signature that was verified. The bogus signature resulted from a compromise of the hash algorithm MD5. MD5 is definitely a weak hash algorithm, but NIST recommended in December 2013 that SHA-1 no longer be used for digital signature as well, even though only theoretical attacks have been produced via hands-on practical attacks. The transition away from SHA-1 has begun. DoD still uses SHA-1 on the CAC, but the upgrade to SHA-2 is being planned. The point of this hash function discussion is that you have to be able to trust the code signature in order to trust the Authenticated Boot service trying to ensure integrity of the software. Once you trust the code, that trust can be passed on to others. The certification service provides remote attestation. The objective is to ensure that only authorized code is running on a system. The idea of remote attestation is it allows changes to the user's computer to be detected by remote authorized parties. The service works by having the hardware generate a certificate identifying which software is currently running, and that information is stored securely in the TPM. Basically, it creates a digital certificate associated with configuration information. The computer can then present this certificate to a remote party to show that unaltered software is currently executing. Digital right management provides a good example. It might involve a user's music player software sending a song to the audio subsystem, but it will only be allowed if it can attest that it is running a secure copy of the music player software. The idea is this provides a more secure path for the music transfer, because trusted software prevents the user from using an illegal player that is recording the music as it is transmitted to the audio subsystem. In a minute, we will talk about a couple of other TPM features, like memory locking, which prevents the music from being dumped to regular disk files, and sealed storage, which curtails unauthorized access to it when saved to the hard drive. The hierarchical instantiation means that TPM can attest to the OS, and the OS can in turn attest to the applications that software is valid. Sealed storage means stored data can only be opened by certain software-hardware combinations. Returning to the music example, users who keep a song on their computer that has not been licensed to be listened to on that hardware will not be able to play it. Using sealed storage, the song is securely encrypted using a key bound to the Trusted Platform module, so that only the unmodified and untampered music player on the licensed computer can play it. Sealed storage depends on an encryption key unique to the configuration, which is based on an endorsement key unique to the machine. The machine endorsement credential is a 2048-bit RSA public-private key pair, which is created randomly on the chip when manufactured, and it cannot be changed. It is burned into firmware. The private key never leaves the chip, while the public key is used for attestation and for encryption of sensitive data sent to the chip. On the Apple commercial mobile devices, they do something similar by tangling the user passcode with the device key in support of encryption. Memory curtaining extends common memory protection techniques to provide full isolation of sensitive areas of memory, for example, locations containing cryptographic keys. Even the operating system does not have full access to curtained memory. For example, a write-only API might allow the storage of private keys via a secure process, but not subsequent reading of that information. The High Assurance Platform, or HAP, is an NSA-sponsored initiative to provide a commercial instantiation of trusted computing. The TPM is a hardware-based root of trust that stores encryption keys and system measurements and protects against software-based attacks. The device measurement feature consists of the identity and integrity of each hardware and software system component being measured and verified at boot time and runtime. For measurement monitoring, verifiable reports of a device's identity and current configuration are transmitted to the network, where decisions are made governing network access and device disposition. Long-term protected storage consists of hardware-based full disk encryption that ensures data is secure even if drives are removed from the workstations. Process separation is based on hardware and software secured virtualization to separate user processes from supervisor processes. Secure domain separation enables the multiple security domains to be hosted on common computing platform base with no unintended interaction. Program isolation is based on guest partitions like virtualization or separation kernels to separate applications from one another. Code, data, and resources associated with Process A are unavailable to Process B. This submodule briefly discussed how the operating system manages resources, enforces access control on those resources, and schedules events. We also delved into trusted computing, which involves additional OS lockdown mechanisms to ensure it has not been modified and is consistently behaving in specific ways. In the next submodule, we will discuss some design principles that try to address OS hardening for both normal systems and more secure trusted systems. This submodule will examine OS design principles for normal operating systems and then overlay some additional requirements for trusted operating systems. We will define a reference monitor, briefly discuss system modes or rings designed to protect the kernel, and some memory protection requirements. Salzer and Schroeder did foundational research on security design principles in 1975, and the principles are relevant today. The notion of a reference monitor was one of the foundational principles. Actually, the idea of a reference monitor was first published by James Anderson in 1972 in Computer Security Technology Planning Study for the Air Force. In that paper, he defined a reference monitor to be 1. Tamper-proof, 2. Always invoked and complete, and 3. Small enough to be validated. The first requirement for a reference monitor requires a kernel that is tamper-proof. If it is not tamper-proof, an attacker could modify the enforcement mechanism of the system, circumventing its security. The second requirement is the reference monitor must provide complete mediation of all security-sensitive operations. If some of these operations are not mediated, then a security requirement may not be enforced. For example, a secret may be leaked or trusted data may be modified by an untrusted process. And of course, mediation must be continuously invoked or it could be circumvented when not active. The last requirement is the reference monitor must be small enough to verify the correct enforcement of system security goals. Otherwise, there may be errors in the implementation or the security policies that could result in vulnerabilities. In their design principles, Sulzer and Schroeder included 2 of these properties as highlighted in the blue box. They did not include the tamper-proof property, although they spent a fair amount of time discussing access control lists, which prevent tampering. The concept of a reference monitor defines the necessary and sufficient requirements for access control in a secure operating system. However, as our cyber infrastructure has evolved, these properties have become more and more difficult to satisfy. As slot counts and features have grown, complexity has become the enemy of the reference monitor. The distributed nature of our computing environment, including the transition to the cloud, may make the completeness property more complicated to satisfy as well, as the access points are often spread across the enterprise, making it impossible to be sure every access is being checked. And as packets travel across the computing infrastructures, they are assessed by packet filters, IDSs, IPSs, antivirus systems, and they may even have to pass through a digital signature validation mechanism, all the enemies of completeness. The least privilege principle is important because it minimizes damage if there is a compromise. Separation of privilege ensures 2-person control is available when necessary, and that a user isn't mixing trusted tasks and untrusted tasks using the same account. For example, a user should not be able to do system administration and surf the web from the same account. The idea of a reference monitor was first defined by James Anderson in 1972 in Computer Security Technology Planning Study for the Air Force. The paper defined a reference monitor to be an access control mechanism that is 1. Tamper-proof, 2. Always invoked and complete, and 3. Small enough to be validated. The first requirement for a reference monitor is a kernel that is tamper-proof. If it is not, an attacker could modify the enforcement mechanism of the system, circumventing its security. The second requirement is the reference monitor must provide complete mediation of all security-sensitive operations. If all these operations are not mediated, then a security requirement may not be enforced. For example, a secret may be leaked or trusted data may be modified by an untrusted process. And of course, mediation must be continuously invoked, or it could be circumvented when not active. Some authors break this into 2 requirements, complete and always invoked. The last requirement is the reference monitor must be small enough to verify the correct enforcement of system security goals. Otherwise, there may be errors in the implementation of the security policies that could result in vulnerabilities. The top red line in this graphic shows complete mediation. Each and every request for a resource is blocked until the reference monitor checks the authorization mechanism and the security policy. When both have been satisfied, the appropriate level of access is granted. This list of protection mechanisms would typically be found in any OS, not necessarily a trusted OS. Some aren't necessarily security mechanisms, but they all work together to ensure the operating system behaves as expected and doesn't generate denial of service conditions. Of course, all OSs require an authentication mechanism to identify users and control access. A subsequent submodule will discuss access control in some detail, including ACLs and C-lists. Access control for virtual memory is even more critical because it is a shared resource. While paging systems and segmentation systems work slightly differently, both must control access to memory by different processes. Enforced sharing ensures all processes have access to resources, and the goal is to guarantee both data integrity and consistency. Object allocation includes both concurrency and synchronization. To understand concurrency, think about threads. This is a property of systems in which several computations are executing simultaneously and potentially interacting with each other. Synchronization refers to the coordination of simultaneous threads or processes to complete a task in order to obtain correct runtime order and avoid unexpected race conditions. A race condition occurs when two threads access a shared variable at the same time. For example, the first thread may read the variable and the second thread reads the same value from the variable. Then the first thread and second thread perform their operations on the value, and they race to see which thread can be the last to write the value to the shared variable. The value of the thread that writes its value last is preserved, while the value of the thread that wrote first is lost. A deadlock occurs when two threads each lock a different variable at the same time and then try to lock the variable that the other thread already locked. As a result, each thread stops executing and waits for the other thread to release the variable. Because each thread is holding the variable that the other thread wants, nothing occurs and the threads remain deadlocked. Fair service ensures no CPU requests and no I/O requests are ignored, creating a starvation situation. Processes sometimes need to communicate with other processes or synchronize access to shared resources, and when that happens, the OS needs to control IPC information flow. This mediation is typically managed via the access control mechanism. OS protection data consists of items like audit data, C-lists, and ACLs, passwords, all of which must be protected. If we narrow our focus to a trusted operating system, we see additional security requirements that must be built into the design. All objects become closely coupled to more fine-grained object access control mechanisms, as opposed to the approach of granting user access to most objects once they have access to the OS. The next submodule will discuss MAC and DAC in more detail, but the key difference is that discretionary access is managed by the owner of the object, and mandatory is based on security clearances, security classifications assigned to objects. Most trusted systems will have a hybrid solution. Object reuse protection is most easily understood in terms of memory. When a user accesses an object in memory, the next user must not be able to access any of the content or metadata from the first user. Everything must be cleared. Total reference mediation means each and every transaction must be processed by the reference monitor. The trusted OS communication channel ensures the user he is talking to the OS, and man-in-the-middle attack vectors have been eliminated. Accountability and audit functionality required trusted systems to keep an audit log of all security-relevant actions that have been taken, but the audit logs may not audit the logging process because the recursion would cause the logs to grow rapidly. Most systems these days have a kernel mode and a user mode. The kernel mode protects the OS and the key OS tables, such as process control blocks, from interference by user programs. However, additional modes may have been implemented in some systems. For example, OS/2 used 3 rings: ring 0 for kernel code and device drivers, ring 2 for privileged code such as user programs with I/O access permissions, and ring 3 for unprivileged code, which is the mode of nearly all user programs. The original Multics system had 8 rings. It was a time-sharing operating system developed in 1965 and used until 2000. The system was started as a joint project by MIT as part of an ARPA effort involving Bell Labs and General Electric. Bell Labs withdrew from the development effort in 1969, and in 1970 GE sold its computer business to Honeywell, which offered Multics as a commercial product but only sold a few dozen systems. The OS has not been used since 2000. Two common virtual memory schemes found in operating systems are paging and segmentation. The OS has to manage access to memory by processes, and in the case of a trusted OS, clear the memory when a process is finished using it. With paging, the OS creates equal-sized page frames, and a process gets divided into pages which are in turn loaded into the frames. This is all transparent to the programmer. With segmentation, the memory blocks are variable. Segment table entries include length and base address, which are used to find a spot in memory. The programmer, especially at the assembly level, has to manage memory, although modern high-level languages do a lot of memory management for the programmer. Segmentation faults occur when data is about to be read or written outside the permitted address space. These are the key memory protection requirements, whether the system uses paging or segments. Access to memory by processes must be controlled. For example, the OS must ensure that two different virtual addresses from two different processes do not point to the same physical address when both processes are running. Memory sharing is allowed among processes, but not simultaneously. If both processes are active, different physical locations must be used, or else one process may corrupt the area of memory being used by the other process. This submodule has provided a brief introduction to properties of an operating system that may provide attack vectors if not properly implemented. Even if properly implemented, a regular OS does not provide all the protection of a trusted OS. The key ideas that we have discussed are: a reference monitor should be complete, continuous, verifiable, and tamper-proof. An OS needs at least two modes, a user mode and a kernel mode that protects the OS and OS tables, and memory protection must be independent of the virtual memory schema. In the next submodule, we will discuss access control mechanisms in some detail. In the field of information security, access control is the management mechanism of the OS that grants or restricts the availability and use of resources. Authorization is the permission granted to access a resource, enforced by the access control mechanism. This submodule will cover the common access control mechanisms found in systems today. While you've discussed these in other classes, this quick review is included because of the close coupling to the operating system. The OS manages the use of all system resources, and its access control mechanism provides the protection for all of the objects in the system. Typically, we think of these files as objects that need to be managed, but we should also include processes and users in that category. Read, write, and execute rights need to be controlled, and of course, the OS has to manage the conflicts and consistency when writing is taking place. For example, when an object is being modified, the OS has to lock it for access by a single subject to eliminate race conditions and ensure consistency. Identification provides a process or mechanism to ensure the subject is who he claims to be. This step sometimes involves providing a picture identification in order to receive a credential necessary to authenticate to a system. Authentication is the mechanism that actually confirms that the credential is valid and trusts that the credential has been closely linked to an identity. For example, to receive a government personal identity verification, or PIV card, you must have a form signed by a government official verifying that a background check has been completed, and you must also present 2 photo IDs to prove you are the person identified on the form. The PIV is a smart card that contains asymmetric credentials that are accessed by a personal PIN. To authenticate using your smart card, you insert it into a card reader and the system will request your PIN. If the PIN is correct, the credentials on the card, such as your authentication certificate and associated private key, can be used to guarantee your identity to the requesting authentication mechanism. Once your identity is known, access can be granted to system resources. Keep the words authenticate and authorize distinct in your mind. Authentication mechanisms validate your identity, and once your identity is confirmed, the authorization mechanism controls your access to the system resources based on your identity. The next submodule will discuss the three most common access control mechanisms: DAC, MAC, and RBAC. For discretionary access control, each object has a unique owner, possibly the creator of the object, who is allowed to grant privileges to access the object to other users. The mechanism can be thought of as a matrix, although it is never implemented that way. The rows of the matrix are subjects who want to access objects, and the columns of the matrix are objects for which access is being managed. So think of an R in a cell of the matrix. The subject in that row is granted read access by the owner to the object in that column. DAC is usually implemented with access control lists, or ACLs. An ACL is basically a single column of the matrix which identifies all the subjects who have access to the associated object as granted by the owner. DAC may also be implemented with capability lists, which is subject-oriented and can be thought of as a row from the matrix. For a given subject, it identifies all the permissions on all the objects that have been granted by the various owners. Because C-lists may be dispersed around the system, they present a greater security problem than ACLs. So the OS usually holds all C-lists on behalf of the users in a region of memory inaccessible to users in order to prevent the user from editing his own C-list. These two implementations provide different administrative challenges. ACLs are easy to administer when permissions on an object change. When a subject is deleted from the system or his permissions change, all the ACLs have to be modified to check for that subject. C-lists are the opposite. They are easy to administer when a subject's permission changes, but not so easy from an object perspective, because the admin has to check every C-list to see which subject has access to the object. This slide shows a model of an access control matrix with subjects from the set S assigned to rows and objects from the set O assigned to columns. Entries in cells grant permissions to subjects to access objects. Notice that the set of objects being controlled also includes the active processes from the set of subjects. So a process can be granted rights to objects, and at the same time another subject can be granted access to the process. To say it another way, some of the subjects from the set S are also objects in the set O. Again, the cells contain rights that a subject is granted on an object, but many of the cells will be empty, indicating the subject has no rights on an object. Because of the prevalence of empty cells, an ACM is never implemented in an OS. Rather, a compressed version like an ACL is used. But the ACM provides a useful model for understanding what DAC means and how it works. Butler-Lampson, in his seminal paper titled Protection, first proposed this model in 1971, and it was refined by Denning and Graham a little later in Protection, Principles, and Practice. These are foundation papers and worth reading for a cybersecurity professional. One of the weaknesses with discretionary access control is it doesn't provide protection from a Trojan horse that has been designed to abuse access privileges. In the example on this slide, we show two files. File F1 has PII regarding user A and is owned by A. File F2 has public information and is owned by user B. As the owner of file F1, A can read and write to the file, but A has not granted those privileges to anyone else. As the owner of file 2, B can read and write to that file, but in this case, B has also granted A the right to write to the file. Now, suppose user A runs a program to edit her personal file F1, and suppose that program contains a Trojan which also runs with A's privileges. The Trojan will be able to read file A and write the contents to file B, because A has write privileges to B. The Trojan has given B access to A's personal information. If the file F1 were classified and F2 were unclassified, this Trojan would be creating a covert channel to steal classified information. The question is, how can the access control mechanism be modified to protect against this kind of a problem? The answer is to implement a mechanism called mandatory access control. This slide is a short reminder of the properties of the MAC model. By the way, mandatory access control is sometimes referred to as lattice-based access control because of the important role played by a mathematical object called a lattice. MAC has two properties that you have learned about in previous classes. Enforcement involves a comparison of security clearance levels of a user's session and classification levels of objects. These are typically the totally ordered set, unclassified, confidential, secret, and top secret. However, the model is robust enough to handle compartments using a partially ordered mathematical relationship embedded in a lattice. The model has two fundamental properties. The first property is you aren't allowed to read documents classified at a higher level than your authorized session. For example, you may have a TS clearance, but if your session is S, you will not be allowed to access TS material. Second, you aren't allowed to write to documents that have a lower classification level than your authorized session. It is assumed that your session has been started at the level of your clearance, but of course, you may be able to start sessions at different levels. We often describe this formal model developed by Bell Padula as the one that constrains you so you can't read up and you can't write down, but you can do the opposite. No read up is usually called the simple security property, and no write down is called the star property. The strict star property means you can only write at your own level. You are not allowed to write up or write down. The model also assumes the presence of a discretionary access control matrix. Let's return to the Trojan horse example, but here we will switch from a concern about PII to a concern about the spillage of classified data. A still has discretionary write privileges to F2, but because A's session was started at a higher security level than the classification level of F2, so MAC blocks A from writing any information to F2, and the classified information is protected. This control is provided by the reference monitor discussed previously, and now you can see the importance of complete mediation to ensure no access attempts are able to circumvent the reference monitor. One of the keys to successfully implementing MAC is that an object's label must not be modifiable. If it is modifiable, a Trojan might be able to switch F2 to a higher classification level, write classified data to it, and then change it back to the original classification level. So in addition to implementing the MAC model, the mechanism has to block any attempts to modify object labels. This is a different view of MAC. It is pretty easy to understand the standard security levels, confidential, secret, and top secret. From a mathematical perspective, this kind of linear relationship represents a totally ordered set. Every level is comparable to another. However, the model for mandatory access control is based on a more general mathematical model involving partially ordered sets, and an example is shown on the right. In both cases, we want the information to flow up, but for a partial order, there are multiple paths, and individual elements of the set, for example Army and crypto, are not necessarily comparable. This is a very important idea for security compartments that may not relate to each other, and there is not necessarily a need to know for members of individual compartments to have knowledge of other compartments. However, even when the compartments do not reside on the same information flow path, the information may flow up to someone at the top who has access to everything. The resulting relationships that develop from using partially ordered sets is called a lattice. The one shown here was developed for a university class project, and it is based on the standard totally ordered set combined with a partially ordered set describing security compartments in part of the Department of Defense. The diagram shows that the identifiers U, C, S, and TS are not obfuscated, but the compartment names have been, probably for security reasons. This was not done in my class, so I don't know many of the details. I do know this diagram is very old now, and I suspect it no longer applies, but it is an interesting view of how complicated the MAC model can be. One important idea that many don't think about is there can be need-to-know compartments at the secret level. It doesn't always require a top-secret clearance to be read into a compartment. The third access control model we will discuss is role-based access control. The first paper describing RBAC was written in 1992, and Sandhu at GMU produced an RBOK framework in 1995 to integrate ideas about sessions and role hierarchies. The key idea is to model the portion of the business logic of an organization. How do they do day-to-day operations using roles people have in the organization? So we have subjects in a certain role doing a certain job, and they need specific privileges to do that job. Ignoring sessions, it is a simple picture. There is a relationship between users and roles, and there is a relationship between permissions and roles. Both relations are many-to-many, and there is no direct connection between users and permissions. This simplifies administration, and that was one of the motivating ideas. If a new employee is hired, the SA can just give her the proper role and doesn't have to worry about assigning her a large set of individual permissions. You can also separate the act of granting user assignments and granting permission assignments to different SAs and/or to different time frames. It allows the organization to customize applications and business logic without worrying about employees. In fact, it is a good way to implement separation of duties. In assigning users to roles, the applications involved don't affect the assignment. However, the nature of the permissions assigned to those roles does depend on the implementation. For example, an OS requires the allocation of read and write privileges. A relational database management system requires the allocation of select and update privileges, and a transaction application might require the allocation of credit and debit privileges. Suppose a user is assigned to a role of professor. He should only be able to see grades of students in his class. But how do you distinguish among all the professors who have the same role? This complexity is addressed by an extension to the framework, adding the concept of constraints on permissions. It allows for the creation of context-sensitive permissions. So permissions and roles are the same for all users, but the actual objects viewed may be different. The idea of a session is that a user may be assigned to multiple roles, but not all get activated when the user logs in. It depends on the configuration file for the session. The session has an ID associated with it, and roles can be added or removed from configuration files for the session. This slide shows the important properties of RBOK. A user's permissions are determined by the role rather than an authenticated identity or clearance. And the extension to RBOK allows roles to encode arbitrary attributes, creating an attribute-based access control mechanism. Policy neutral means an RBOK mechanism can be reconfigured to model and support both DAC and MAC. However, you cannot use RBOK to do MAC if it doesn't include the abstraction of a session. And the user role relationships and the role permission relationships are both many-to-many. I have reviewed the three most common access control mechanisms: discretionary, mandatory, and role-based access control. DAC is identity-based, and the owner of an object manages permissions. MAC is based on the allocation of security or privacy levels to users and objects, and RBOK is based on permissions assigned to user roles. They are quite different models that represent an evolution in our understanding and security needs. Each has its benefits, but they have different security postures. Often we see a hybrid model that includes both DAC and MAC, and RBOK mechanisms can be modified to model either. The need-to-know constraint is often enforced using DAC overlaid on another mechanism. Finally, RBOK can be extended to provide ABAC if additional access control complexity is a requirement. In the next submodule, I will discuss some of the attacks that have leveraged vulnerabilities found in OS implementations. For the most part, these attacks are well understood and are no longer available to the attacker, but they haven't been eliminated entirely. And for sure, many of the concepts involved are reused in attacks on more modern designs. This submodule will present some of the historical attacks on systems that were successful due to weaknesses in the OS. One of the key ideas that appears over and over is buffer overflow attack. While we have implemented many changes in our implementations to address buffer overflows, we still see them on almost a daily basis. That putting more information into a buffer than it can hold remains a common and successful attack approach. This is a very important concept to understand, and we will pursue it in some depth. This is a list of the attacks we will review in this submodule. Many of these examples are taken from Operating System Security by Trent Yeager. Examples of network-facing daemons in Linux that provide access via network ports are SSHD, FTPD, and SendMail. Processes that are network accessible and don't protect themselves from remote input are susceptible to remote attack, especially buffer overflow attacks. Some of the remote login daemons that have been too trusting are Telnet, rlogin, FTPD, and NFS. An example of excessive trust is insecure versions of FTPD that sends passwords in the clear. Another example is an insecure version of NFS that accepts any response from a remote file system as being from a legitimate server. So one inference we can draw from these vulnerabilities is it is important to check remote input very carefully. Of course, this isn't a new message. We saw it previously in the web exploitation module, especially in preventing SQL injection attacks. The second message is not to trust the network. Attackers may be sniffing packets or spoofing legitimate network nodes. This is another message we have seen previously in the network exploitation module. Windows calls kernel extensions kernel mode drivers, and Linux calls them loadable kernel modules or LKMs. These are object files that contain code to dynamically extend the running kernel of an operating system without recompiling. Without LKMs, an operating system would have to include all possible future functionality compiled into the base kernel. Much of that functionality would be unused but consume resources and memory. LKMs typically add support for new hardware or file systems, but they can also be used to add system calls. They may be unloaded in order to free memory and other resources when no longer needed. Both types may allow an attacker to execute code in the kernel with full system privileges because the attacker takes advantage of root-owned processes with access to the kernel. Of course, a kernel module cannot be loaded by just anyone. Only a user with root privileges or the kernel itself may load or unload a kernel module. That means it can't be leveraged before you get root, but once you have it, it is very useful for loading backdoors and rootkits. By using a loadable kernel module, the attacker does not need to inject Trojans into system functionality. Rather, he can subvert the functionality at kernel level without leaving a trace. This approach also subverts tools generating system fingerprint hashes. And attackers have learned how to make the LKMs invisible and unremovable. Environment variables allow processes to convey state, and the buffer overflow example we will explore in the following lectures will leverage this by creating a new environment variable to convey state, and the information passed will consist of shellcode. Another way an attacker can use environment variables is to change the lib path so that the OS checks for and runs malicious code instead of the expected code. In other words, a trusted process may invoke malicious code. In the submodule to follow on setuid, you will explore this idea by getting a normal process temporarily running as root to run privileged code because the lib path has not been properly managed. We have discussed the idea of input validation multiple times, but it is worth repeating because it represents a critical attack vector into systems that do not do an adequate job of checking. One of the critical elements to control is the location of libraries and host paths. If validation is not done, directory traversal vulnerabilities may exist. This may create a vector for attackers to gain authorized access to restricted directories and files. These input validation problems are typically vulnerabilities in web servers or application code, allowing an aggressor to exploit the system in order to read or write files that are not intended to be accessible. In some situations, an attacker may be able to execute arbitrary code or system commands. The last bullet on the list is also critical because it prevents buffer overflows. The idea is to always make sure that any input of any kind received in an application is never longer than the buffer it is supposed to fit into. The Heartbleed bug in OpenSSL is a good example of weak input validation, although not strictly a buffer overflow attack. During the TLS Keep Alive handshake, the attacker was able to request an extra 63 kilobytes of memory because it was assumed the protocol would be used properly, and there was no validation of the length of the string returned as the payload. In some cases, the extra memory that was returned contained session cookies that allowed an active session to be hijacked. Suppose an untrusted process guesses the name that will be used as a trusted process's temp file in the /temp directory. Since any process, trusted or untrusted, can create files in /temp, the attacker creates his own file there using the name just guessed for the trusted process. The attacker then grants access to the trusted process to access his untrusted temp file. So now when the trusted process creates a temp file, it will already exist, and the attacker has access to it since he created it, and he is able to read the trusted process's temp file. In software development, time of check to time of use, or TOC2, is a class of software bug caused by changes in a system between the checking of a condition, such as a security credential, and the use of the results of that check. It is a kind of race condition. An inode stores all the information about a regular file, directory, or other file system object, but it is loosely coupled to the file name, which creates an attack vector. When an attacker requests access to a temp file, he passes the file name to the trusted process for an access control decision. For example, he may say he wants access to his temp file /temp/x, which will be granted. The call to the access function behaves as expected and grants the program the necessary permissions to access the file. However, both functions, access and fopen, operate on file names rather than on file handles. That means there is no guarantee that the file name still refers to the same file on disk when it is passed to fopen as it did when it was passed to the function access. If an attacker replaces /temp/x after the call to the function access, but before calling fopen with a symbolic link to a different file, the trusted process will open the file even if it is a file that the attacker would otherwise be unable to access. A reminder, a symbolic link is a reference to another file as an absolute path, which affects path name resolution. Passwords are not stored in the clear. Rather, they are typically salted and hashed before being written to the shadow file. However, there is no guarantee the cryptographic mechanisms can't be attacked. Non-standard and unvetted algorithms are dangerous and should never be used. For example, the use of a proprietary cryptographic algorithm is subject to reverse engineering, and if there is a weakness in the algorithm because it hasn't been reviewed properly, it provides an attack point. Similarly, any modifications to the hash functions to speed them up may create vulnerabilities. We know MD5 is a weak hash function, and the Flame virus leveraged this to create a fraudulent certificate to digitally sign some malicious software so it would appear as if it originated from Microsoft. The attack is called a chosen prefix collision attack, in which a new bogus certificate is created and the hash of two different certificates, one good and one bad, produce the same result during signature validation. An important point in applying algorithms is that given the same seed, the pseudo random number generator always produces the same random output stream. This is actually leveraged by some wireless protocols, but it also means two applications using the same seed are subject to cryptanalysis. And an obvious problem in applying algorithms is still sometimes overlooked by programmers: the failure to destroy plain text after encryption. LAN Manager is a network operating system developed by Microsoft, but there are multiple issues with the authentication protocol. Passwords are not case sensitive, so all passwords are converted into uppercase before generating the hash value. In addition, password characters are limited to a subset of the ASCII character set. Both of these issues reduce the attack surface significantly. Password length is limited to maximum of 14 characters, but a 14-character password is broken into two halves of 7 characters each, and the hash is calculated for the two halves separately. So the attacker only needs to brute force attack 7 characters twice instead of 17 characters. This makes the effective strength of the password equal to twice that of a 7-character password, which is significantly lower complexity. If the password is 7 characters or less, then the second half of hash will always produce the same constant value. Therefore, if the length of the password is less than or equal to 7 characters, the password strength can be determined visually. The hash value is sent to the server on the network without salting, making it susceptible to man-in-the-middle attacks, such as replay the hash. Wi-Fi protected setup, WPS, is vulnerable because the specification did not require a timeout to eliminate brute force attacks. Some vendors implemented it, some did not. In addition, WPS has a weakness similar to LAN Manager that speeds up the brute force attack. The PIN is only 8 numbers, and one of those is a checksum reducing the brute force attack to 7 numbers. The 7-number string in the PIN is divided into substrings of 4 numbers and 3 numbers for validation, reducing the attack surface from 10 to the 7th, or 10 million attempts, to 10 to the 4th plus 10 to the 3rd, or 11,000 attempts. VxWorks has a weak default hashing algorithm that is susceptible to collisions, so any string that produces the same hash is good enough to be authenticated. For example, y bracket 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 ks hashes to the same string as password. The result is an attacker can brute force a correct password by guessing a string that produces the same hash and access the relevant service. Again, this reduces the attack surface. I demonstrated the vulnerability of a bootloader in the first submodule, but I have not talked about the other 2 bootstrap issues. Sun OS allowed booting into single user mode, and after getting root privileges on the box, it was possible to extend those privileges to the server. In other words, access was granted to the whole network. If you have physical access, it is sometimes possible to boot from either a live CD or a USB stick and get access to the system's disk. A Windows system executing on a PC can often be rebooted with a foreign operating system like Linux. Once the foreign system is booted, the NTFS volume may be mounted and accessed since the attacker has bypassed the access control mechanism enforced within Windows. This is a good way to steal a Windows password file. In the Department of Defense, Security Requirements Information Guides provide guidelines for development of Security Technical Implementation Guides, or STIGs, which contain lockdown information. STIGs, developed by the product vendors, document applicable DoD policies and security requirements for specific technical products, as well as best practices and configuration guidelines. The Defense Information Systems Agency, or DISA, is in the process of replacing the SRG process by developing DoD appendices to the National Information Assurance Partnership Protection Profiles, although there is still a requirement for a product-specific STIG. The result of the NIAP Common Criteria Evaluation will be used to formulate a STIG. STIGs will be published in XCCDF format to enable consumption by automated tools, where both compliance can be assessed and configuration remediation addressed with the addition of OVAL code. STIG compliance may be assessed from across the enterprise using host-based security system and a Security Content Automation Protocol compliance checker. In Windows, registry entries may have a security context, and unfortunately, some programs leave the security context at any. When this happens, any normal user can change the paths and use registry entries to gain administrative rights and compromise the system. Windows users may have administrator privileges, but may not understand the significance of those privileges. Accounts are often configured that way so software will install properly and execute. That means it is easy for an unknowledgeable or careless user to install malicious software with a single click. Bit9 is one product that provides tools to control the installation of software. but it is sometimes configured to be too strict, and users get totally frustrated trying to get their work done. In the situation where users have administrator privileges, compromising any user account will give an attacker root. In order to motivate our deep dive into buffer overflows, here are a couple of old but famous examples involving the Windows IIS web server. The code red overflow vulnerability was magnified by the fact that the indexing service was enabled by default in IIS. Similarly, SQL Server came enabled by default, even though it may not have been running. The code red worm leveraged a buffer overflow vulnerability in the indexing server that allowed instructions to execute to produce worm behavior. Basically, IIS mishandled the HTTP request and executed the included packet with full permissions. Interestingly enough, a patch had been released for IIS about a month before the worm appeared. Those systems that had been patched were not affected. This happened in 2001 before administrators were so vigilant about installing patches. In fact, Microsoft had failed to patch their update server, and some users got infected while trying to patch. A couple of years later, Slammer leveraged a buffer overflow in SQL Server, which is bundled with IIS and was initially configured as enabled. A side effect was a denial of service because the worm propagated so fast that it clogged routers and shut down many sites. Again, a patch had been released 6 months earlier. In this submodule, we have discussed several OS attack vectors. These have all been well understood for some time, but when new software is written, some of these get created anew. So we need to think about them as both pen testers and system defenders. As users of ethical hacking skills, we can use our knowledge to help improve system defenses. If you go to the National Vulnerability Database on the day you view this lecture and do a search on buffer overflow, you will most likely find at least one buffer overflow vulnerability identified within the last 7 days of your search. Before starting a deep dive into buffer overflows, we will spend some time on SetUID, which is a necessary but sometimes vulnerable feature of operating systems. SetUserID or SetUID is an object flag that allows users to run programs with temporarily elevated privileges in order to perform a specific task. If you can break out of the task when you have elevated privileges, you may gain access to objects that you are not supposed to have. This submodule will explore some examples of SetUID vulnerabilities. SetUID is a flag that can be modified using chmod. As noted earlier, it allows users to run programs with temporarily elevated privileges in order to perform a specific task. It is needed for tasks that require higher privileges than those which common users have, such as changing their login password. When the password is being changed, you temporarily have root privileges. Here is an example. If you do an ls-tac-la in user/bin, you will probably see the sudo program. Look carefully at the permissions and you will see it has the SetUID permission bit set on the executable. Some versions of Linux use color coding to identify SetUID programs. For example, on my Debian system, SetUID programs are highlighted in red. This bit indicates to the kernel that the program should always be executed with the UID of the owner of the executable file. In the case of sudo, that is root. Once sudo is running as root, it can do the necessary authentication and SetUID syscall before the fork to invoke the requested command. The internal field separator bug is a good example of how SetUID has been abused in the past. The attack idea is that a program with temporary root permissions can be fooled into executing user-supplied code. To see this, suppose you set the IFS to / instead of blank. Next, the malicious code is created in the current directory and named bin. When the program makes a system call running the function system/bin/ls, rather than traversing the directory path to find the binary, the program bin would be run from the current directory, and it will be run with root permissions. This bug has been fixed by making sure shells do not inherit the IFS variable. The change file mode or chmod command lets you modify file permissions. The first digit selects the set user ID, set group ID, and restricted deletion or sticky attributes with values of 4, 2, and 1 respectively. The second digit selects permissions for the user who owns the file. Read as 4, write as 2, and execute as 1. The third selects permissions for other users in the files group without write privileges, and the fourth for other users not in the files group without write privileges. To explore SetUID, if you haven't done so already, you will need to build a VM using something like Debian, Ubuntu, or another Linux version of your choice. It really doesn't matter which flavor you choose, but Kali won't work because you are always running as root. Once you get the VM running, check to see if Z-Shell is installed by trying to run it or looking for the executable in /bin. If it is not present, install it. You will also need to compile some simple C code, so check to see that the GCC compiler is installed. You can just type GCC without a file name and see if it tries to run, or it is usually found in /user/bin. If it isn't on your VM, install it. This submodule requires completion of a hands-on lab designed to explore the SetUID flag to see how poor programming practices create vulnerabilities. In fact, due to potential security issues, many operating systems ignore the SetUID attribute when applied to executable shell scripts. The lab has 4 parts, and I have provided a detailed lab sheet that provides you specific guidance on what needs to be completed and documented with screenshots. The first 2 parts involve a comparison of a binary's behavior when the SetUID bit is set and when it is not. The last 2 parts require you to compile a C program, which I have provided. One program will investigate the vulnerabilities of relative directory paths when the SetUID bit is set. The other program will demonstrate that even a well-written program can be leveraged when running with temporary root privileges. We have discussed several aspects of OS security to include important design approaches and access control mechanisms that help secure OSs. We also looked at unsecured bootloaders and SetUID programming errors as possible attack vectors. Most of these problems have been around for a very long time. We understand them and our systems are getting better, but there are still techniques routinely discovered that compromise operating systems. The next lecture will be on rootkits and provide guidance on how to develop one.